In this video, I want to discuss how to solve any inequality in one variable. This method will work great when solving linear inequalities, absolute value inequalities, quadratic inequalities, polynomial inequalities, and with a minor adjustment, it can be used to solve rational inequalities. So how do we solve any inequality in one variable? And we start by considering the inequality, and any inequality can be written in this form. We have something on one side and something on the other side with one of the inequality signs in between. So either the left side is less than the right side or the right side is less than the left side. So here's how we solve any inequality in one variable. We replace the inequality sign with equal sign. Then we don't have an inequality anymore, we have an equation in one variable. If you solve this equation in one variable, then you should be able to produce what we call the solution set. So the solution set is just the set of values that make this equation a true statement. So what you do next is you take this solution set and you plot it on the number line. So in this case I have 3 solutions, so I'm going to have 3 points on the number line. And the fact is that each of these subintervals that we created by plotting the solutions of the equation is either entirely part of the solution of the inequality or entirely excluded from the solution. How do I know if it's a solution or not? Well, to answer the question whether this interval is entirely included or entirely excluded, we just have to pick one point, which we call test point. So on each of these intervals, we pick a test point. And we take that value and we test our inequality. So if inequality is true, we can write here true. If inequality is false, we can write here false. We can write here false. And let's assume inequality is true over here. So intervals on which inequality is true are entirely part of the solution set of the inequality. So at this point, all I have to do is just describe these intervals using the interval notation and put them together in the answer. Now, what about the boundary points? We include the boundary points only for non-strict inequalities. So the inequalities that have signs like this. So let me show you an example real quick. Let's take some absolute value inequality. And let me show you how this approach works with this inequality. Step 1, I'm going to replace inequality with equal sign. And I'm going to solve this equation. Now, of course, to solve absolute value inequality, you have to be good at solving absolute value equations. If you make mistakes solving absolute value equation, you won't be able to solve absolute value inequality. So to solve this absolute value equation, we isolate the absolute value and then we divide, we split the equation into 2. one with positive and one with negative 6. So the solution set is 7, negative 5. Next, I take these two values, negative 5 and 7, and I put them on the number line. So now I have 3 intervals. And from each of these sub-intervals, I'm going to pick a test point. And I'm going to test my inequality. Remember, you have to test your inequality, not your equation inequality. So let's test it at negative 6. Negative 6 minus 1 plus 1, is it less than 7? So we have absolute value of negative 7 plus 1, less than 7. That's false. Let's test inequality at 0. 0 minus 1 plus 1 less than 7. Absolute value of negative 1 plus 1 is less than 7. That's true. Let's test the same inequality at 8. That's false. So it turns out that our inequality is true only on the interval from negative 5 to 7. So that's my answer. Now I have to make a decision about the boundary points. Do I include them or do I exclude them? Since this inequality is strict, I do not include the boundary points. So this is my answer. So this is how this method works for example, absolute value inequalities. Let me show you how it works for polynomials. So let's take a simple polynomial equation. Inequality. Something like this. So to solve this inequality, again, according to this method, I have to replace the inequality sign with equal sign. And how do we solve polynomial equation given to us in factored form? Well, we use the zero product property, so we conclude that it's either x minus 1 equal to 0 or x plus 2 is equal to 0, which means that x is equal to 1 or x is equal to negative 2. So these 2 points divide now the number line into 3 subintervals. On each of these subintervals, now I pick a test point. And at each of these test points, now I test my inequality. Now, when you're testing your inequality with polynomials, and most of the inequalities that you'll have to solve will have 0 on the right side. That means it suffices to just keep track of the sign of the expression. So we don't have to actually compute the entire expression. We can just keep track of signs, whether it's plus or minus, and based on that decide whether the overall expression, whether it's positive or negative. So at negative 3, so if we plug in negative 3 to the polynomial, here's what we get. And what I said is that we don't need to know the exact value, we just need to know that this is negative, but negative squared is positive. So is this true? When you take negative and multiply by positive, is that positive? No. So this is false. Let's test it at 0. If you plug in 0, 0 minus 1 is negative, 0 plus 2 is positive. Positive squared is still positive. So now we have negative times positive. Is that positive? Nope, it's still negative. Now if we take x equals 2, at 2 we have 2 minus 1 is positive, and 2 plus 2 is also positive, and we also have it squared. So everything is positive, so the inequality is true. So this simple analysis means that the only subinterval that is part of the solution is this one. So the answer is from 1 to infinity. Now, do we include the boundary points or not? In this case, we do include the boundary points because inequality is not strict. So not only I have to include 1 as a boundary point, I also have to include 2 because 2 was also a boundary point. So this is the solution set to this polynomial inequality. So next I want to show you how and what exception we have to make when we're solving rational inequality. So let's consider the rational inequality. So let me go over the method first, and I'll do a quick example. When you have a rational inequality, the way we solve it is by first writing it in this form. So this is the only way we can solve rational inequality, as if we write it as a fraction on one side and 0 on the other side. So what we do next is we solve the equation made from setting the denominator equal to 0. So that's going to produce a solution set. And at the same time, we solve an equation made from setting denominator equal to 0. And that also may produce a solution set. So now, to solve inequality, what we do is we combine these two solution sets. So the only difference when between solving rational inequalities and any other inequalities is that now we also have to include the points at which the denominator is equal to 0. That's the only difference. The rest is the same. So the way we pick the test points, the way we test the test points is literally the same as before. But with this minor adjustment, we can apply the same method and start solving rational inequalities. So let me show you an example here. So if we take this rational inequality and we solve it using this method, then we have to solve x plus 2 equals 0, x minus 3 equals 0, and we have to get x equals negative 2, x equals 3, and we have to put it on the number line. So we have 2 points that divide the entire number line into 3 subintervals. Let's pick a test point. And just like with polynomials, in this case we don't have to evaluate the fraction, we can just keep track of the sign of that fraction. So for example, at negative 3 plus 2 is negative, and negative 3 minus 3 is also negative. So I'm not computing this, I'm just looking at the sign. So negative over negative is positive, so inequality is false. Now at 0 we have positive divided by negative, then it's true. And at 4 we have positive divided by positive, which makes this inequality false. So the only interval on which this inequality was true is between negative 2 and 3. So negative 2 and 3 is my solution set. Now I just have to decide whether to include the boundary points. And since inequality is non-strict, I have to include the boundary points, but the boundary point that came from the solution of the equation in which denominator was set equal to 0 cannot ever be part of the solution set. So we never include that point in the solution set. So I do include negative 2, and I do not include 3. So this is how we solve any inequality in one variable. This method is called the test points method, and it works for any inequality in one variable with the minor adjustment for rational inequalities.